Okay. So, as I announced, so we will have no class on April 22. Okay. So because of I need to attend the evaluation. So the but unfortunately, so the next week is the midterm exam period. So you can study. You can study for this course and then also other courses. Okay. And then the midterm exam will cover until what we will learn in this class, for today's class, right? Uh, Also, the midterm exam is the closed book exam. So no cheat sheet is allowed, no cheat sheet. And then, no electric devices are allowed. So no electric devices except the simple calculator. Okay, you cannot use a smartphone, obviously, right? And then, so we will take the exam in this classroom, right? And then any other information? No, okay. So during the regular class time. So the exam will start 10:30 exactly. So please be seated before the exam. Okay, that's it. So we will take the midterm exam on April 24, right? The next Thursday. Okay. So any questions about the exam? Okay. So in the previous class, we learned about the digital design conventions. Okay, so as I mentioned in chapter 4, we will learn about the hardware architecture of RISC-V CPU. So because this is hardware, so you need to understand how to design the hardware, right? It means the digital systems. It is because the CPUs are a kind of CPU is a kind of digital systems, right? So but actually the important concept is that where is the this is so actually so you need to understand how the clock period is determined. Okay, so as I mentioned, between two flip-flops, so there is a combinational logic, and then the delay of this combinational logic decides the clock period of this digital system. Why? Because the clock period is larger than the delay, the longest delay of this combinational logic. So you need to understand that the delay of combinational logic decides the clock period. Then why clock period is critical? It is because of where is this equation, right? So this equation is so important, right? So the execution time is proportional to the clock period. So we need to actually, when we design CPUs, then we need to reduce this clock period, right? Okay, so you need to understand this. And then now, so we will learn about the single cycle processor architecture. So in the previous class, we learned about some required steps for executing instructions. And then I mentioned the 5 steps. So instruction fetch, instruction decoding, execution, memory access, and write back. So not all instructions, but the most instructions require these 5 steps. So which means we need to implement the hardware that support these 5 steps for executing instructions, right? So we can combine. So actually, in order to design the required hardware, so firstly, we can design the basic component, so very simple component. Okay. And then we can just connect the input and output ports of these components. So that's what we learned in the digital logic design course. So in order to build a complex logic or complex hardware, so firstly, we can design the simple components, right? And the simple modules. And then we can just connect the input and output ports of these modules. And then we can build complex the hardware or complex systems, right? So it's the same. It's the same to the CPU design. So I mentioned that. So in order to execute the instructions, we require 5 steps. So instruction fetch, instruction decoding, and execution. And the memory needs to be accessed by load and store instruction and write back. Okay, these 5 steps are required. Then how can we build some simple module or basic components, and then how can we connect these modules for implementing this hardware, the CPU. So firstly, instruction fetch. So I mentioned that for instruction fetch, we need to use program counter, right? And the program counter is a register. So it means that the program counter value is stored in this register. And then using the program counter, we need to access the memory, right? And then because the memory contains instructions, so so we can use the PC as the address of memory. Then we can get an instruction. So if we just give address to memory, then we can get data from memory, right? So we can get instruction, and then instruction decoding is instruction decoding step includes the decoding of instruction and register file access. What does that mean? So for example, add x1, x2, x3. If a CPU execute this instruction, then this instruction requires 2 operands from registers, right? So it means using this register number, we need access. So like the memory, so we can give register numbers to register file. So register file is the group of registers. So you can understand that this is a very small memory, right? So if the register number is given to this register file, then we can get the data in the target registers, right? So during the instruction decoding step, we can access the register file, and then what is the execution? The the required operations. The required operations are executed. So for example, add instruction requires add operation. So it means it requires adder, but so in ALU includes the required operations. So we can use the ALU, but in order to execute these required operations, so we need to also provide the operands. So for example, the add operation need to perform add, but in order to perform add, so we need the 2 operands, right? So and then actually we get 2 operands from register file, right? So these operands are given to the ALU. Then the ALU is the combinational logic, right? So input operands are given, then we can get result. So this is the result of ALU. So result. And then memory. So we need to access. So load was store instructions, access memory, right? So address with the computed address, and then we can compute the address using the source register and immediate value. So so we can get address, and then using this address, we can access the memory. Okay, and then what is the write back? The result. Result data is written back. Written back to the register file. Then, firstly, we can define which components are required. So, for example, in our instruction fetch, we require program counter register, and we require memory, right? So because the instructions are in the memory, but we assume the instructions are in the instruction memory, right? So it is in the instruction memory, and for instruction decoding step, during the instruction decoding step, so we need to access register file. So obviously we require register file, and then execution uses ALU, so we require ALU. So we can list required hardware components, right? So like the program counter register, and memory, register file, ALU, data memory. So memory during the memory step, we can access the data memory. Then we can just connect. We can just connect the input and output ports, of this component. So for example, this is the program counter register. And then I mentioned that the program counter value in this program counter register will be used for address. Then what should we do? We can the output of the program counter register is program counter value, is a PC value, right? And then we can connect this output to the input of memory, right? So because it is used as the address of instruction memory. So we can just connect the output of a program counter register and the input of instruction memory, because this value is this data. This value or this data is transferred from output port to the input port, right? Do you understand? So this is given, and then we can get instruction, and then using the instruction, so we learn how to encode instructions, right? So, and then, the instructions includes the register numbers. That's what we learned in chapter 2, right? Instruction encoding. So instructions includes the register numbers. So using the register numbers, these register numbers are given to the register file, right? Then we can get operands from register file, and the operands are given to the ALU. So like this, we can just connect the input and output ports of hardware components. Then we can just build the very simple CPU based on these steps, right? So like this. Also, so usually if the next instruction is executed, then PC is just updated by PC plus 4, right? So this logic is also required. And then also we can jump to the different target using the branch instructions or jump instructions, right? So this adder is also required. Then we can just connect these components, right? But so in this figure, you can find that the wires are just connected like this, right? But so actually in the hardware, hardware design, this is not allowed. Why? The wire is just metal, right? So so, so I believe some of you learned about the electric physics in the high school, right? So so wire, if the wire is connected, the wire is the conductor, right? So which means the voltage level of this wire is the same. So another wire is connected to this wire, like this. Then the voltage level of these wires, so this one, this one, are the same, right? Because this is the metal, right? The wires, okay? So metal wires. So the voltage levels are the same. So what's the problem? Digital design, we represent we represent the digital values using voltage levels. Then how about this? The two wires are connected, but we can know that. So actually this wire, this line has the value of PC plus 4 because this is the PC output from the program register, and then PC is added by 4. So this is the PC plus 4. And then as you can see, so this line, this wire has the PC plus some value, actually PC plus immediate. Because as I mentioned, this adder is used for calculating the target of branch instructions or jump instruction. What's the problem? If we just compare this wire and this wire, the values are different. So it's a PC plus 4, and then this is the PC plus immediate value. What's the problem? This is not allowed because in the hardware design, if two wires are connected like this, then these wires need to have the same values, right? Right, because I mentioned that the wires are metal wire, and then it needs to have the same voltage level, means the same data, right? So this is not allowed. Then how can we handle these connections? Oh, where is so? Oh, okay. Oh, it's not allowed. It's not explained. So actually, it's also this slide explains this. Okay. So as you can see, the wires are connected. So actually, at this point, we need to use the multiplexer, right? So it means, so for this point, so this line is the PC plus 4, and then this line is the PC plus immediate. So, these data are different. And then if these data are different, then we need to use the multiplexer, and then using the selection signal, we need to select the one signal from these two different values. Okay. So actually, for this point, we need a multiplexer. Okay. So multiplexers are required. Okay. So this is some basic, the overview of the single cycle processor design, and then I will explain the detailed design of the each steps. Okay. Okay. So firstly, I will define the terminology data path. Okay, data path data path means elements that process data and addresses. So you can understand that data path elements are hardware components that process digital values or digital data and addresses. Okay, addresses for memory. So you can just understand that data path is kind of some modules for the hardware modules, and then actually these modules are combinational logic. Okay, and then it receives the input values. So input values are also data or addresses, and then if we just use this module, then it generates the output data. So it's similar to the combinational logic. Okay, so receive the digital data, and then it generates the output, digital output. So we can call these are data path element. Okay, so as I mentioned, so we can just define these data path elements, right, for performing some required steps, and then we can just connect these data path element. So we can just connect the input and output ports. Okay, so this is some basic design, the basic hardware design process. Okay, okay. So instruction fetch. So instruction fetch. So what are required operations? Instruction fetch. The PC is updated. So usually for the next instruction, the PC is the oops. PC is the PC plus 4. And then using the PC, we can access the memory, instruction memory, and then we can get instructions, right? So these are the operations in instruction fetch step. So we have a program counter, and then, this is the 32-bit register, because we are learning about the 32-bit computers, right? And then, so this is the PC. So this is the PC value. The output of the PC register is the PC value. And then, as I mentioned, this PC is connected to the address port of instruction memory. So instruction memory has instructions, and then we can get instruction. So what is the bit width of this instruction? So what is the bit width? So, this is the 32-bit, right? I mentioned that this is the 32-bit register. So PC value is the 32-bit. So we can use this 32-bit PC value as an address of this instruction memory. Then instruction memory will generate so actually we can get the instruction from the instruction memory. Then what is the bit width? What is the bit width of this instruction? So right? What is the size of instruction of RISC-V? The 32-bit, right? 32-bit. It's 32-bit data, right? So that's why this is the PC plus 4, right? Why? The 32-bit is the 4 byte, right? So which means, so in order to access the next instruction, we need to, because the size of instruction is 32-bit, then we need to access the next instruction using the PC plus 4. The address is the difference of address between the current instruction and the next instruction is 4, usually 4 for the RISC-V, right? Then this is the PC plus 4. And then PC plus 4 usually becomes the PC of the next instruction. Okay. So this PC plus 4 will be used as the program counter value of the next instruction. I mentioned usually because if we do not execute the branch, then we can use the PC plus 4. So otherwise, then we need to generate or calculate the target program counter, right? So this PC plus 4 will be used as the PC of the next instruction. So actually, it is synchronized with the clock signal. So this PC, so you need to you need to distinguish the program counter of the current instruction and then the program counter of the next instruction. So this PC, the output of the program counter register, this PC is the PC of the current instruction. Okay, so we using this PC, we can access the instruction memory, then we can get the instruction. So obviously, this PC value is the program counter of the current instruction. Then what is this PC? So this is the PC plus 4, and then this PC plus 4 is given to the input of the program counter register. So this PC plus 4 is obviously the PC of the next instruction. And then when the next instruction is executed, in the next clock, right? Right? So the program counter is synchronized with the clock, like the D flip-flop, right? So, and unlike the software model, so we need to consider the timing, the timing of the digital signals, right? So we need to, which means we need to identify, this is the data for the current instruction, and then this is the data for the next instruction. And then also, these data are synchronized by clock signals. Okay. So this is an instruction fetch step, and then so I will. So I'm showing the behavioral model. So this is the system verilog statement. It's a statement because it's not a module. Okay. So what can you see? This module explains about the program counter, the behavior of program counter register. So as I mentioned, this is the PC register. And then, this is the 32-bit register. Then what is a register? So in the digital logic design course, we learned that a register is a group of D flip-flops, right? A register usually. So we can use this terminology register for different meanings. So sometimes we can use the register as the group of D flip-flops. Also in CPU, we use register as some temporary memory space for storing data. So we learned about the general purpose registers, right? Like from X0 to X31, right? So the register can have some different meanings, right? But in the digital design, so when I mentioned the PC register, so this is and also when I mentioned the 32-bit register, so it represented this is a group of D flip-flops. Okay. So this is the 32-bit register. So as I mentioned, this register, the PC register contains 32-bit PC value, the program counter value, and then the current PC. Current PC is the output of this PC register. And then next PC will be prepared. Okay? So you need to understand this. And then we can implement this PC register using system Verilog like this. So system Verilog just describes the behavioral model of hardware, right? So I because this is the first time, so I will explain this statement. So you know, this is the PC underbar core. So what does that mean? So as you can see, this is the PC value, but this is the PC of current instruction, right? So because that's why I added the underbar curr, CURR. And then as you can see, the number of bits, the bit width of this signal, this is the logic, this signal is 32 bit, right? And then, so the always underbar FF. So what does it mean? This is the sequential logic. So it means D flip-flop actually. Positive edge of clock or negative edge of reset underbar B. So it will be synchronized with the clock signal, and then it will be reset by reset underbar B. So this is the negative reset, right? And then if the reset underbar B is 0, then it is initialized as 0, right? Else means it's the normal state. So for the normal state, PC curve will be updated with the so this is the gray colored because this is PC underbar curve plus 4. So as I mentioned, so we need to understand the timing. So now so we are in the hardware world. The hardware works in the real world, and then the real world, in the real world, we need to consider timing, the time, right? So as I mentioned, the PC is the program counter is synchronized with the clock. So actually this value is the PC of the next instruction, like PC underbar next, right? But this value will be updated the rising edge of the clock. So you can understand like this. So rising edge of the clock. So this is the current clock period. We can use the PC curve, the PC underbar curve, right? So, and then during this current clock period, we calculate the next PC. It means the program counter for next instruction, the PC plus 4, right? We just compute. And then this value is updated. So it means that the output of a program counter register is updated by this value at the rising edge of next clock. Okay? Then we can execute the next instruction. Okay? So during the current clock period, we execute the current instruction using the PC underbar curve, and then for the next clock period, then the PC is updated with the PC curve plus 4, and then this value is given to the PC on the core, then we can just execute the next instruction. Okay. So you need to understand this. But as you can see, this is the actually identical to the deep flip-flop, right? So where is the okay? Actually, the identical to the this statement or this module, right? So you can just understand that the program counter register is deep flip-flop. So actually, we implement the deep flip-flop. The 32-bit register is a deep flip-flop. So PC. And then instruction memory. I mentioned that the memory is the array. Okay. So what does that mean? An array includes multiple elements, right? And then in each element, we can store data, right? And then in order to access a certain element, we need to identify the index of the target element. And then using this index, we can access the target element, right? This is the array. So you can just understand that a memory is array. So instruction memory or data array indexed by an address, right? So you can just understand memory like this. So this is the high level model actually, okay? It's the abstracted model, okay? So we can use the address as the current PC, right? So like this one, okay? So we can use the current PC. And then, so which means address, this is the index of element. So in this example, so I defined the data array in instruction memory. And then as you can see, so this is the bit width of each element. So what does that mean? An element can contain 32-bit data. Okay, so this is the bit width of one element. So then what does that mean? It just defines number of elements in an array. And then this element will have index from 0 to 255. So what does it mean? This array called a data has 256 elements. And then each element size is 32-bit. Okay? Do you understand? Then what is the size of this memory? So size of one element is 4 byte, right? It's because it's 32-bit. And then there are 256 elements. So 1024 bytes. Each 1 kilobyte. Okay. So this example shows that. So I define 1 kilobyte of instruction memory, right? Then how can you access the output of the instruction memory? So I mentioned that the address is the current PC, right? This is the PC of the program counter register. So we can just like this data and then PC, right? But what is this PC? This is the PC underbar curl, right? Because in this example, I define PC underbar curl, right? So actually we can use the PC underbar curl as the index of data. Then what is this DR? DR is the instruction. Okay. But actually for the next labs, I'll provide some components, but actually, so I will provide the module, the instruction memory module. And then, the input of this instruction memory module has the input name is the address. So actually we need to use the address here. Okay. Okay. So this is the instruction memory module, but uh, I showed this system verilog statement because so based on this programming language, this is the hardware description language, and then actually it's a programming language. Then you can just understand. You can just understand the behavior of this hardware module. So think about the programming language. So you by reading the programming language, we can understand the behavior of our code, right? We can just define the plus, minus, and then for loop. So if we read the code, then we can understand the behavior of this program. Hardware is the same. By reading the hardware description language code, we can understand. We can understand the behavior of this hardware. That's why I show the system verilog statement in this slide, right? Okay. Okay. So this is the instruction fetch. So the instruction fetch includes the program counter and the instruction memory. What is this add? Add is already implemented in this part because this plus, right? Right. Okay. And then R-type instructions. So R-type instructions require, so for example, so two source registers and wait a second. So the R-type instructions require two source registers and then one destination register. For example, add x1, x2, x3. So this is the RS1, so source register number 1. And this is the RS2, source register number 2. Now what is this? This is RD. So R-type instructions need to access registers, and then it accesses 3 registers, right? And then I mentioned that the register file. So register file is the group of registers. And then also this is the array. This is an array. And then each register includes the 32-bit data. So you can just understand that the register file is the very small memory, right? So register works like this. We can just give the register numbers and then we can get register data. But in order to support the R-type instructions, we need to have 2 source registers and then 1 destination register. Source registers are used for reading data from registers, right? Destination register is used for updating data in the target register, right? So, the purpose is different, right? So the registers receive the 3 register numbers in order to support the R-type instruction, but 2 read register number. So you can find the read register 1 and read register 2. So this is the RS1, RS2, and then for write operation, receive the RD, destination register. This is the write register number. And then based on this RS1 and RS2, we can get read data 1, 2. Then what is the bit width of this port? What is the bit width? This is identical to the bit width of a register, right? A general purpose register. What is the bit width? It's the 32-bit. Because we are learning about the RV32I, right? Also, What is this bit width? Bit width is the 32 bit, right? So actually this port, the write register port and the write data port is used for write operation to the register, and then read register 1 and read register 2, and then read data 1, read data 2. This is the output. These ports are used for reading data from registers. Okay, so this is the register, and then in order to support the register write, register file includes the reg write control port. So which means if the reg write is 1, then write operation is performed. Okay, so it also has the control port. And the ALU is simple. ALU receives the 2 operands. So what is the size of this bit? This port? Obviously 32 bit. 32 bit. What is the output? ALU result. It's a 32 bit. Okay. So ALU received the 2 operands data, and then it generates the output data, the 32-bit output based on the ALU operation control bit, because ALU can perform the many different operations such as add, sub, exclusive or, and, or, blah, blah, blah. Okay, because, and then we need to select the one of operations from these supported operations. So this is the control signal for ALU. Then ALU generate the output and then the zero detection signal. Okay. So this is the review of the encoding rule. So as I mentioned, so this is the R-type instruction encoding rule, right? All right. And then you can find the RD, RS1, RS2 here. So what does that mean? This number, register number, is stored in these fields. So in order to access register file, then we can just connect this 5-bit to the RD port. So write to register port, RS1 connected to the RS1 port. Okay, so read register 1 port. RS2 is connected to the RS2 port of the register file. So we can simply connect the register numbers in instruction, because instruction includes these data, the register numbers. So we can just connect the part of instructions, so these fields, to the registers, right? Register file. So as you can see, the instruction is here. So instruction is the output of instruction memory. Then, but you can find that instructions are connected to this register number port, right? So it means this is the RS1, RS2, RD, but only the part of instruction, because as I mentioned, the instructions includes this information, the register numbers. So we can just connect the part of instruction. For example, the instruction bit, what is this bit? The 12 down to 8 to the RD port. Okay. Then let's see the behavioral model of register file. So as I mentioned, the register file is an array of general purpose registers. And then in a RISC-V, we have X32 general purpose registers from X0 to X31. So we can, like the instruction memory, we can define an array. So you can find that the array name is the rf underbar data. And what is this part? So because we have 32 general purpose registers, so this number is 0 to 31 because it means identical to the x0 to x31, right? And then the size of a single register is 32-bit. So it supports 2 register read, the source register, and then it supports 1 register write. And then this register write is controlled by reg write signal. Okay. For the write operation. So actually, when we design a single cycle CPU using system Verilog, the register file is also synchronized. So it is because it includes the write operation. Okay. And then this write operation is performed at the before the rising, just before the rising edge of the next clock. Okay, so it should be synchronized. So otherwise, then we will get incorrect result for some specific cases. Okay, so this is the write operation. So at the rising edge of the positive clock, if the regular write is 1, then what is this value? What should be here? So RF data will be updated. So it means RF underbar data will be up. So which element? It is indexed by RD, right? RF data RD. So this is the target register for the write operation. Is updated by which value? This one, write data. So write data. Oops. Write data. So it's actually the data input of the register file. Okay. It's similar to the array operation, array write, right? And how about the read operation? Read operation is simply RF data and RS1, right? Because it's indexed by the the source register 1. So is it true? Is it correct? So usually correct. I mean, for the most case, it's correct, but it's not always correct. Why? Because of x0. So we learned that x0 always contains 0, right? So do you remember? So in order to support this behavior, so we need to consider this condition. So which means if RS1 equals 0, then it is 0. Oh, otherwise, this is question mark. Otherwise, it's the RF underbar data and RS1. Okay. Right. Do you understand? Because of x0, right? Okay. So, and then behavioral model. So ALU just generate the result from 2 operands, and then ALU is controlled by ALU operation. Okay. So this is the combinational logic. Okay. So, and then we will learn about the ALU in the more detailed, so in the later. And then load store instruction. So what is required? The load store instruction read register operands. So usually the load is the I type instruction, and then store is the SB type instruction, right? But anyway, load and store instruction requires the RS1, right? And then we need to perform RS1 plus immediate, right? To generate, and then we use this as the address of data memory, right? So this is the data memory. So, this the data memory, and then this data memory also received address. So this is the memory, and then we can read data. So for the load instruction, we use this read data, and then also for store instruction, we just store data to the memory. So we use write the data port, okay? And then also, we need to calculate the RS1 plus immediate. So the immediate, we need to use the immediate generator. Now, where is the immediate data? On instruction. An instruction also includes this immediate data. So for example, the load instruction has the 12-bit 2's complement numbers, right? So, and then in order to calculate the RS1 plus immediate, then we can use the ALU, right? But where is the ALU? If we see the ALU, then we can find that ALU receives 32-bit input operands. What should we do? Also, and then ALU needs to perform. So RS1 is the 32-bit data. It's a 32-bit data. And then immediate is the 12-bit data. So actually, in order to use the ALU, the immediate needs to be extended. So we need to make 32-bit data from 12-bit immediate number, right? So what is required? Sign extension. So we need to increase the number of bits from 12-bit to the 32-bit. Then the immediate number is the 12-bit signed data, the 2's complement number. So in order to extend this 12-bit data to 32-bit data, we need to apply sign extension, right? That's what we learned in the number system. No, not number system. It's chapter 2. Okay. So this is the I format, I type data. Okay, immediate is here. So we can know that we can get immediate data from an instruction, right? And then, so as I mentioned, we need to generate 32-bit data from 12-bit immediate number. But we learned that. So actually, for the different instruction type, the immediate data can be stored in the instruction with the different forms, right? That's what we learned. So in the I-type instruction, in the I-type instruction, the immediate data is here. The S-type immediate is here and here, right? And then B-type is more complex, right? Is stored like this. So we can use the 12-bit immediate numbers from instruction, but based on the different instruction types, then immediate data has the different forms, right? So, which means we need to apply different type of sign extension, right? So but the I type and S type is similar. So for in order to generate the 32-bit data from the I type instructions, the immediate data is here. The instruction bit number 31 down to 20, and then 31 is the sign bit, right? Because it's 12-bit, right? So we just repeat the sign bit 20 times. Then we can generate this is the 32-bit data. Do you understand? So I just apply sign extension for the immediate data. S type, immediate number is here and here. So we can use the higher part. No. The, the higher upper part, and then lower part. Upper part of immediate number and lower part of immediate number. Okay. So instruction 31 down to 25, and then instruction 11 down to 7. And then in this example, 31 is the sign bit. So we can just apply the sign extension. B-type. B-type is different. So that's what we learned. Okay. So B-type, so for the immediate B-type, the immediate numbers are always multiple of 2. And then I mentioned that the RISC-V 0 is not stored in the instruction. So we need to add the 0 in order to generate the 32-bit number. So this is a little bit tricky because the rule, the encoding rule is more complex, right? And then based on this rule, then you can just add the instruction. But instruction 31 bit of instruction is the sign bit. So we just extend the sign bit, but 19 times because 0 is inserted here. Okay, so this is the immediate generator. So immediate generator received instruction, and then so I type, S type, B type instruction, and then from the immediate number from these different types of instruction, it generates the 32-bit number, right? And then this generated number is given to the other port, this port of ALU. Do you understand? Okay, so it looks like this. So from the instruction, we can the part of instruction is given to the immediate generator, and then immediate generator generate the 32-bit immediate number, and then this number is given to the ALU. So in order to select this port and this data, we need to add the multiplexer here. Okay, this is how the immediate generator works. Okay, and then data memory. So data memory is also the memory, right? So it's the same. So the data is an array, and then it has we assume that each array has the 32-bit data, and then write operation also requires the synchronized with the write clock. Clock, the clock signal, and then the mem write. Using the mem write, we control the write operation of the data memory. Okay, so data, and then read operation. So we can get the read data from this data memory. Okay, so it is controlled by the memory read. The memory read signal. If the memory read is 1, then we can get the data from the memory using we can use the address as the index of this data. Otherwise, it's 0. Okay. So branch instruction. So branch instruction like BQ, X1, X2, and target. So branch instruction reads 2 operands from register file. And then in order to calculate the target, so we can just calculate the target as the PC is the PC plus immediate number, right? This is the behavior of branch instruction. So I already explained how the immediate number is generated from for the B-type instruction, because BQ is the B-type instruction, right? So from this B-type instruction, we can generate the 32-bit data from the immediate number using this rule, right? And then it's so sign bit left 1. It just to explain that it's the last B0 from the 32-bit generation, right? So and then it is added with the PC underbar core. Okay, and then this is the 32-bit data from the immediate generator for B-type instruction. Then we can calculate the branch target, because for the branch instruction, PC is the current PC plus immediate, right? So we can just calculate the target of branch instruction. Then what is also then what should we do? So what is the other operation? What is the other required operation for branch instruction? So we can just calculate the target of branch instruction, but we need to compare 2 source registers, right? So for example, BQ, we need to check X1 is equal to X2. Then if X1 is equal to X2, then PC next becomes the PC underbar core plus immediate. Otherwise, PC underbar next is equal to PC underbar core plus 4. Right? So this is the behavior of branch instruction, right? So what is required? Comparison. Comparison is required. So in order to compare 2 values, we need to perform x1 minus x2, right? And then we can just check this is 0 or not. So what is required? Subtraction is required. Then the branch instruction performs subtraction like x1 minus x2 using ALU. But the branch instruction also needs to calculate the PC plus immediate, right? That's why the branch instruction includes in order to execute the branch instruction, we require additional adder. This ALU is used for comparing 2 source registers. Okay? Do you understand? So this is the branch instruction. So by combining these components, we can build the single cycle processor, the full data path of the single cycle CPU like this. So we can, as I mentioned, we can combine. So I explained about each step, the operations of each step in the previous. I explained, and then by combining these steps, we can build the full data path of the single cycle processor, right? So, and then, but what is it? What is it included? So you can find the multiplexer here, and then multiplexer is here. So as I mentioned, if the two different, if, if we select from the two different data, we require multiplexer. And then, so what does it mean? This blue colored text. So you can find the black colored text here, the inside of the Datapath element. And then actually these black colored text represent the data input and data output, right? And what is this blue colored port? It's the control port. Okay, so these Datapath elements like the registers, memory, data memory, and the ALU multiplexer includes the control port. So we need to also control these Datapath element using this control port. Okay. So in this figure, I just showed the full Datapath element. So which means I just combine the Datapath elements to build the single cycle processor. But the control port are not connected. So which means we need to generate the control signals for this control port. Okay. Okay. So I will stop here, and then as I mentioned, the midterm exam will cover until this point, right? The full data path of the single cycle processor. Okay, and then so thank you for your attention, and then good luck for the midterm exam. 감사합니다.